I've got two parallel plates here. The left one is positive, and the right one is negative. I've got a positively charged particle over here at the left-hand plate. It's moving with an initial speed, for whatever reason. It's got an initial speed of 1.0 times 10 to the 4 meters per second. What's going to happen to that charged particle as it's released near that positively charged plate? Good. It's going to accelerate toward the negative. Now, I got another question for you. I got a car at the top of a hill here. It's got an initial speed of 10 meters per second. What's going to happen as I release that car at the top of this hill? It's going to accelerate toward the bottom of the hill. We're going to treat these two problems virtually the same way. Okay, in the second case here, this is what we saw a lot in Physics 20, right? Cars accelerating down a hill. We treated that as a conservation of energy problem. We had no issue with that, no problem with that whatsoever. The car initially had potential energy, gravitational potential energy, because it has a height, and it initially had kinetic energy because it had a speed. It was a combination of potential and kinetic energy, which was converted, we're looking for the speed at the bottom of the hill, entirely to kinetic energy, 1/2 mvf squared. So essentially what we're saying here is, although we started off with a little bit of kinetic energy, we had a net conversion of potential to kinetic energy. We had less height at the end than we did at the beginning. We had more speed at the end than we did at the beginning. A conversion of potential to kinetic energy. The exact same thing happens over here. When this charged particle speeds up, it's like the car going down the hill. Its EI is equal to EF in the same way. Its potential energy plus kinetic energy, because it's moving, is equal to the final energy, kinetic. But what we're going to do here is sub out the MGH, and we're going to sub in QVI. QV is the electric potential energy. It comes from the equation for electric potential. V is equal to E over Q. We're just rearranging it to get E is equal to Q times V. Remember, not electric field is equal to Q times V, but electric potential energy is equal to QV. So we're going to say potential energy, just like over here, potential energy, plus kinetic, just like over here, kinetic, is equal to the final kinetic energy when it reaches this other side there. I want you, every time you see a charged particle speeding up, to think a car is going down a hill. Okay? I say that every year now for the last, I don't know, however long it is since I've started using this analogy. And it works. But still, as much as I tell people, think of it as the car going down the hill, still people refuse to do that. Okay? Still people will say, I know better. I'll do it my way. I know better. Okay? You know what? You don't. You don't know better. Okay? Think of it as the car going down the hill, and picture it as the car going down the hill. And do this like you would do in Physics 20, like you were good at in Physics 20. And then just sub in at QV wherever you see MGH. All right. The other situation is when we have, let's make the plates diagonal this time. We got a positive plate right here. We got a negative plate right here. We've got a negative particle right here at the positive plate. It's got an initial speed. Let's make it again. 1.0 times 10 to the 4 meters per second. What's going to happen to this this negative particle as it's released at a speed of 10,000 meters per second near this positive plate? What's going to happen to it? Going to move anywhere? Well, it's moving toward the negative plate, right? It's going to keep moving toward the negative plate, but as it does that, it's going to slow down. Maybe it stops somewhere. We don't know, right? Just like a car at the bottom of a hill with an initial speed of 10 meters per second slows down as it goes up the hill. Now, maybe it stops somewhere on the way up the hill. We don't know. It depends on how high the hill is and so on. But the bottom line is it slows down. Here, in this case, we've got a conversion. Instead of potential to kinetic like we had in the last example, we've got a conversion of kinetic, which we have at the bottom of the hill, to potential, which we have at the top of the hill. Now, there may also be kinetic energy there as well. Again, it depends upon whether it's still moving when it reaches the top of the hill or still moving at whatever point it is that you're analyzing it, right? Right here, whatever. Might be kinetic energy at the end, might not be. Depends on whether it's still moving. Over here, same deal. Same deal. We're going to say EI is equal to EF. This is like a car going up a hill. Okay, the charged particle slows down. A car is going up a hill. We start off with kinetic energy when the car is at the bottom of the hill. We end up with, well, potential energy when the car is at the top of the hill, and maybe kinetic energy as well when it's at the top of the hill. It all depends upon whether it's still moving or not. Only difference, we're going to sub out MGH, and we're going to sub in electric potential energy, Q times V. That should be VF, not VI. That make sense? All right, we're going to do a problem right now, and when you see this problem, okay, forget about the diagram that's given in the problem, the parallel plates and so on. I want you to think of it, if the charged particle is speeding up or slowing down, I want you to think of it as either the car going up, down the hill, or up the hill. Again, depending upon whether it's speeding up or slowing down. Take a look at this question. 11.10 on 571, it says, a pith ball, sometimes we see this term and I just assume that you know what it means or that it doesn't really matter. In the end, it doesn't really matter what a pith ball is in this case, but sometimes a strange word throws people off, whether or not it's really relevant. Pith is a material, a really light material from the inside of a plant, and it's really good in electrostatics experiments, partly because it's so light. So just a little ball that's good for experiments involving electric charge. You can see that it's really light. It has a mass of 2.4 times 10 to the negative 4 kilograms. It has a positive charge. Probably should circle that positive, okay, because that might be relevant. It's initially at rest at position A. So I'm going to write in here at position A, V is equal to 0 meters per second. At this point, the charged pith ball has 3 times 10 to the negative 7 joules of electric potential energy. Okay? We're told that it has this much potential energy. When it's released, the ball accelerates. That's a big deal. Okay? When a car is released and it accelerates, when the car accelerates, it must be going which way? Up the hill or down the hill? Down the hill. Because if it's speeding up, you're not going to speed up as you're going up the hill, right? It's going down the hill. Okay, car going down the hill. Position B, it has this much potential energy. It has less potential energy at position B. That makes sense, right? A car goes down a hill, it has less potential energy the further it goes. The more kinetic energy, the further it goes. We want to find the speed of the pith ball when it reaches position B. We want to find the speed of the car, right? Starts off with a certain speed, okay, starts off with a certain height. We want to find the speed of the car partway down the hill. Not all the way down the hill, because we haven't reached the bottom of the hill, but partway down the hill, where we still have some potential. Okay, if this is the problem right here with the car going down the hill, then we're going to set it EI equal to EF, because that's what we do when we have a car going down a hill. The initial energy in this case would be potential energy, because the car is at the top of the hill. It's got potential to roll down the hill, but we've also got kinetic there because it's moving at the top of the hill. Or is it? No, it isn't. Begins at rest, right? Tells me here the car, okay, using that term loosely because it's a pith ball, right? But for the analogy, the car is at rest when it starts. That means the initial energy is entirely potential. At the end of the problem, though, when it's about halfway down the hill, we've got potential energy left, and we've got kinetic energy. Now, strictly speaking, this isn't MGH, right? But what do? If we're thinking of it as a car going down the hill, we can write in MGH literally, and then sub it out, and then sub in QV. Now, most of you are probably not even going to write in MGH. You're just going to go straight into writing QV, and that's okay. You don't have to write in MGH and then erase it and then write in QV. But I do want you to think of it that way. Think of it as, okay, what kind of energy does the car have? Gravitational potential energy, and so on. Okay, and then if you, even in your mind, sub it out, sub in QV. Now, they've actually simplified this question for me a little bit, because they've told me that the initial potential energy here, QV, is 3 times 10 to the negative 7 joules. I don't need to multiply Q times V, because I've got the value of QV already. I don't need to sub in QV final, because I've got the value of QV final already. It's 1.5 times 10 to the minus 7 joules. I've got the initial and final potential energy. Okay, the only reason I plug in QV or MGH, as the case may be, is to find the initial and final potential energy. Is that 10 to the negative 8 or 10 to the negative 7? Oh, it is 10 to the negative 8, you're right. Couldn't make that out. Thank you. So that is 10 to the minus 8. First one is 10 to the minus 7? Yeah. Plus 1/2 of 9.11 times 10 to the minus 31 times VF squared. I'm sorry? Oh, you know what? It's not the mass of an electron. Hey, careful there, right? Probably a good idea, actually. Dallas, good point. Might be a good idea to circle that in red when you see it, because I just made one of the most common mistakes ever. And I didn't do that on purpose, okay, to make a point to you. It just happened, right? I put in the mass of an electron. Okay, 2 of the most common mistakes that people make in this unit is when we're dealing with something other than an electron, to use the charge and or the mass of the electron. Why? Because we use those so often. It's habit, right? That was my problem. It's habit to use an electron, so I just plugged in the mass of an electron. If that's a multiple choice question, good chance my answer pops up there, right? But it's wrong. So you're right, Dallas. Thank you. It's 2.4 times 10 to the negative 4 for the mass there. All right, let's calculate this on the calculator up here so that we can all see how exactly you arrive at the answer there. We're going to say 3 times 10 to the minus 7 subtract 1.5 times 10 to the minus 8. Then we're going to multiply that by 2. Then we're going to divide that by 2.4, was it? Times 10 to the minus 4. 2.4 times 10 to the minus 4. And then we can't forget to square root that. We end up getting 4.87 times 10 to the minus 2. It should be 4.9 actually times 10 to the minus 2, 2 digits, right? Is that okay? Besides the 2 silly mistakes that I made there, right? One was not really a silly mistake. I just couldn't read that number so well. Besides making it 10 to the minus 7 joules, where it should have been 10 to the minus 8 joules, the silly mistake, making it the mass of an electron instead of the mass of the pith ball. Besides that, not such a bad question, right? We can get that question right. Okay, if you can analyze the car going down the hill right over here in physics 20, boy, oh boy, oh boy, physics 30, we should be able to do the same thing, but sub in QV wherever we had MGH. Okay, that's what I want you to do. Okay, you got a couple questions that I want you to work on right now. We'll give you maybe 5 minutes to work on these questions. Maybe not enough time to quite finish them. Maybe not. It's going to be close. And then after that, we'll do one more example, which will finish off the unit for us. So see what you can do with these over the next 5 minutes-ish. All right, let's take a look here. Number 1 says a negative charge is at rest in the field of a larger positive charge. It's got this much potential energy. When it's released, it accelerates. Okay, charged particle accelerates. That's like what? When a charged particle speeds up, that's like a car going down a hill, right? Good. So if a charged particle is going down a hill, we've got a conversion of potential energy to kinetic energy. Potential decreases, kinetic is going to increase, right? If we analyze it as a conservation of energy problem, EI is equal to EF, clearly we start off with potential energy, MGH. It's at rest so it's got no kinetic energy. It accelerates. We want to find the kinetic energy of the negative charge just before it strikes the positive plate. In other words, we want to find the kinetic energy. We want to find the kinetic energy when a car reaches the bottom of the hill, or just as it reaches the bottom of the hill. So it's going to be only kinetic energy at the end of the problem. Now, we're going to replace mgh with qv. And since we're looking for the kinetic energy and not the final speed, let's replace 1/2 mv squared with just ek. See what I'm doing there? We don't need to put in 1/2 mv squared when all we're looking for is the value of ek. If we're looking for speed, well, then we got to replace it with 1/2 mv squared. There's an even bigger simplification here. Right? We've got the value of qv as well. We've got the value of the initial potential. It is potential, but its value is 3.2 times 10 to the negative 12. So would you look at that? No calculation involved. The final kinetic energy is equal to the initial potential energy, 3.2 times 10 to the minus 12. Some of you may have recognized that without even writing anything down. Okay? Hey, wait, we start off with this much potential. It's all converted to kinetic. Well, that's how much kinetic we have. Okay? And that's fine. If you can think of it that way, that's fine as well. Number 2. A small sphere with a charge of negative 2 microcoulombs. I'm going to circle that, actually, and I'm going to circle that microcoulombs as well, just in case it's relevant. It accelerates from rest toward a larger positive charge. It accelerates. It speeds up. Car's going down the hill. But the car started off at rest. So what do we got here? We've got initial energy that's potential. No kinetic at the beginning here. It accelerates toward a larger positive charge. The speed of the sphere just before it strikes the positive charge, the speed of the car just before it reaches the bottom. So in other words, we've got just kinetic energy at the bottom of the hill, or when the charged particle gets to the other side. 5.2 times 10 to the 4. How much potential energy did the negative charge lose? Well, started off with this potential energy, and now it's all kinetic, so that's how much it lost. Let's just multiply 1/2 times the mass times the speed squared. So as it turns out, we didn't need to know that that was a negative charge, or we didn't really care that it was in microcoulombs. We just circled it just in case, because usually that matters, obviously. Right? Make sense, guys? Okay, let's do one more example, and then that'll end it here for us. Page 572, 1111, make a wish. Okay, 1111. 2 vertical parallel plates are connected to a DC power supply as shown in 11.36. The electric potential between the plates. Hey, this sentence, there's something wrong with. It's not phrased right. There's a typo in there. What should it say? The electric potential between the plates is 2,000 volts. What should it say? The potential difference is 2,000 volts. One of the plates could be 2,000 volts. The other plate could be 0. One of them could be 6,000. The other plate could be 4,000. One could be 18,000. The other plate could be 16,000. Okay? Bottom line is, we don't know. We don't really care about that. The potential difference is 2,000 volts. We're not going to lose any sleep over that typo because it's not really going to affect us, but strictly speaking, it is potential difference. Okay, here's this sphere with the positive charge. It's placed at the positive plate and released. All right. We're told it accelerates toward the negative plate. But what if we weren't told that? A positive charge is placed at the positive plate. What's going to happen to it? What's going to happen to it? It's going to repel away from the positive plate. It's going to speed up, right? We know it accelerates without being told that. If it accelerates, if it speeds up, if a charged particle speeds up, we're going to think of it as the car going down the hill. Now, it started at rest, I think, didn't it? Yeah, it's placed there, so it's going to start at rest. Okay, we're going to start off with potential energy, and that's it. We want to find the speed the instant before it strikes the negative plate. We want to find the speed of the car when it reaches the bottom of the hill. So it's kinetic energy. But we're going to sub in QV for MGH. Remember in the last couple of questions we did, we had the value of QV, so we just put in EP for it. But here we have to actually go to that step and put in QV because we don't have EP already. Q is 2.6 times 10 to the minus 12 coulombs. Not a bad idea. Not a bad idea for me to have circled that when I read the question, because it's not the charge of an electron. I didn't make the same mistake as I made in that other question, but I could have. Wouldn't be the first time, it won't be the last time that I'll make that mistake. Now, the initial potential, is it 2,000? We actually don't know what the initial potential is. But we do know what the potential difference is. We could say the initial potential is 2,000, final is 0. We could say the initial potential is 4,000, and the final potential is 2,000. We could say the initial potential is 10,000, the final potential is 8,000, but we'd have to have potential energy at the end in that case. What's the easiest thing to do? If the potential difference is 2,000, then it's easiest just to say what, Brad? Yeah, to make the initial 2,000 and the final 0. So let's say 2 times 10 to the 3. What do we got here for the mass? 3.0. Probably wouldn't have been a bad idea to circle that in red as well. All right, let's do this on our calculators as well to make sure that we can all do it. We've got 2.6 times 10 to the negative 12. Multiply that by 2,000. We're going to multiply that by 2 to take the half over. We're going to divide it by 3 times 10 to the negative 15. And we're going to square root that. We end up with 1.86. We're going to round it actually to 2 digits, so it's going to be 1.9 times 10 to the 3 meters per second. Is that okay? All right, a little bit of homework, just a little bit of homework for tonight. Page 572, questions 1 to 2.